Let's talk about AOPS Introduction to Number Theory 5.32. There are 2,000 cells in a particular gel. The cells are numbered 1 through 2,000, and each contains one inmate. One night, while all the inmates are asleep, a series of 2,000 computer glitches occurs. First, the computer unlocks all the cells. Then, the computer turns the locks of every evenly numbered cells. 2, 4, 6, etc., relocking only those cells. The computer then turns the locks of every third cell, 3, 6, 9, etc., through the first 2,000 natural numbers, where for each natural number n, the computer turns the locks of the cells that are multiples of n. 2 questions here. A, for a cell numbered m, which of the 2,000 glitches affects that cell? B, how many of the prisoners will awaken to unlock cells? Let's tackle A. So, for a random cell numbered m, which of the 2,000 glitches affects that cell? Well, we know from the question, which is quite long in this case, but not that hard to understand, that the nth glitch unlocks all the cells that are multiples of n from n to 2,000. So, if we want the nth cell to be affected, then we want numbers that are factors of m. So we want numbers that are factors of m to be the glitch. Okay, so let's say m was 60. 60 has quite a lot of factors, so yeah. Well then, which glitches would unlock or affect 60 in the 60th cell in any way? Well, obviously the first glitch would, because it unlocks every cell. And then there would be the second glitch, because it's a factor of 60, so 2, 4, 6, 8, 10, and then all the way up to the 60th cell. And then the 60th cell would be, affected, right? The third cell, the fourth cell, the fifth cell, the sixth cell, the 10th, 12th, 15th, 20th, 30th, and 60th cell. These are all the cells that would affect the 60th cell. These are all the glitches, that would affect the 60th cell. Why? Because these glitches are factors of 60. So, for example, if you took 12, the 12th glitch would unlock would turn the locks of the 12th, 24th, 48th, and 60th, so on, cells. So it's just all the factors of 60. And 60 isn't that special except for having many factors. So similarly, for any other m that is a natural number from in between 1 to 2,000, the glitches that affect that cell would be factors of m. Okay, so moving on. Okay, so that's the answer. Moving on to B. How many of the prisoners will awaken to unlock cells? So at the end of the 2,000 glitches, right, how many cells are still unlocked? So how do we know if a cell is unlocked or locked at the end of the 2,000 glitches? Well, it depends on how many times the lock has been turned, right? There's only two situations that a cell could be in, unlocked or locked, in this question, unless the lock gets stuck or broken or something. But yeah, in this question there's only 2 situations. And at first, before all the glitches happened in the first place, obviously these cells were locked. So you go from locked, which we'll use with L, to the first glitch where everything is unlocked. Then after some other glitch, locked, then unlocked, then locked, then unlocked, right? Every time there's a glitch, the situation flips. Every time there's a glitch that is a factor of the cell number, then the situation flips. So notice that. So this is the first glitch. Okay, on the first glitch that this cell experiences, it turns unlocked. The second glitch the cell experiences, it's locked. Third, locked. Third, unlocked. Fourth, locked. Fifth, unlocked again, etc. So the odd number glitch that this cell experiences makes it unlocked, and an even number glitch that this cell experiences makes it locked. So how many glitches are there in total? If there are an odd number of glitches in total, say 5 glitches that the cell experiences in total, then the cell would be unlocked at the end of the 2,000 glitches, right? If there's an even number of glitches the cell experiences in total, then the cell would be locked by the end of the 2,000 glitches. And how do we know the number of glitches that a cell M experiences? Well, we already know from A that for a cell numbered M, the glitches that are factors of M would affect, like, lock or unlock this cell M. So clearly, the amount of glitches are the factors of M. So we take M equals 60 as an example. It has a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 factors. So if that's even, so at the end of the 12th glitch that affects the 60th cell, M equals 60 will be locked. So how many, and similarly, if M has an odd number of factors, which means it experiences an odd number of glitches, it would be unlocked. So how do we determine the number of factors from 1 to 2,000 quickly, right? We don't really want to list out everything and then count one by one. That'd be like really, really slow, since there are 2,000 numbers, not 2, not 20. Well, notice that for numbers like 60 or 30 or 20 or 22 or 10 or even 2,000, these factors are paired up. Like for any number, factors are paired up, right? Because factors are basically A times B equals M. A and B are both factors if they're like integers. And here we're talking about positive integers because these cell numbers are positive. So if A and B are positive, right, then these two are factors. So factors come in pairs. So usually there is an odd number of factors, unless in the special case of where M is a squared number. Why? Because then in this case M equals C squared. Now C and C pair up together, but C is just one number, right? So that counts as one factor, not two. Which in this case, one pair of these factors that M was supposed to have turns into one factor, not two. So, and since all the other factors are still pairs, because these other factors are all different from each other, then M has an odd amount of factors. So for example, 9, right? These factors 9 has are 1, 3, and 9. So where are the pairs? 1 times 9 is 9, and 3 times 3 is 9. 3 times itself is 9, so 3 is like a pair, but it's a single factor. Hopefully that makes sense. And then basically for all of these square numbers, they have odd factors, and that's like a property here in number theory. So I guess you should like memorize it or at least understand it, you know? So, how many square numbers are here then? That's what the problem is. How many square numbers are from 1 to 2,000 inclusive? Now, 45 squared is 2025. Because I guess like I just memorized it, okay? So 45 squared is 2025. And 1 squared is obviously 1. So 2025 is bigger than 2,000. So we have 1 squared to 44 squared. 44 squared is like, I'm pretty sure it's like 1936 or something. But either way, it's smaller than 2,000. So we have 44 square numbers here from 1 to 2,000 inclusive. So 44 prisoners would awaken to unlock cells. So 44 is the answer.